Did you know that the moon is rusting? No, not rustic, rusting. Well, that sounds impossible because rust needs oxygen, and the moon, well, it doesn't have it. Or so we thought. Apparently, Earth is leaking its air, and it's marinating the moon. It might have been like that for billions of years. What does this mean? And why do scientists say it's great news for a future lunar base? Well, let's find out. A few years ago, the Indian Space Research Organization sent a probe called Chandrayaan-1 to orbit the moon. Its mission was to take some nice pictures, but it also was carrying a NASA-built instrument designed to chemically map the surface. The readings came back showing something scientists didn't expect on the moon – hematite. It's an iron oxide, or in plain words, rust. It's the same red, rusty material that eats through your garden fence or a forgotten bicycle chain. Finding rust on Earth is normal because our planet is wet and airy. You need a strict recipe to make it happen. You need iron, you need water, and you need oxygen. The moon already has the first ingredient for rust because its surface is rich in iron from billions of years of asteroid impacts. But the other two ingredients are missing. There is no atmosphere to provide oxygen, and there is no liquid water gathering on the surface. But it goes beyond that. Space actually hates rust. The sun constantly blasts the moon with the solar wind, a stream of fast particles made mostly of hydrogen. Well, these particles tend to strip oxygen away from rocks instead of adding it. All of that makes it obvious why hematite doesn't belong anywhere near our satellite. But these results don't lie. The presence of hematite means that somehow, despite the vacuum and the sun's particle stream, the moon is getting a steady supply of oxygen. It's not coming from deep space or the lunar core. Also, the rust isn't spread evenly. The data showed that the hematite is more concentrated on the side of the moon that faces Earth. The far side is mostly clean. Now, the only oxidizer close enough to do the job is Earth. We learned at school that Earth's atmosphere ends at the Kármán line, about 62 miles up. That's where space officially begins. But that's just the thick part. In reality, Earth is wrapped in a gigantic invisible cloud of hydrogen called the geocorona. It's enormous. It glows in ultraviolet light, and it stretches almost 400,000 miles into space. That's farther than the moon's orbit. This means that despite being very far away, the moon is still within the outer edges of Earth's atmosphere. If you were standing on the moon, looking back at Earth with a telescope that can see ultraviolet hydrogen, Earth wouldn't look like a blue marble. It would look like it's wearing a huge, fuzzy, glowing halo. Now, when we picture Earth and the moon, we imagine a huge, clean gap between them. Two worlds separated by nothing. But that nothing isn't actually empty. The two are already connected by gravity, tugging on each other nonstop. But there's another kind of connection most people never think about. Earth is surrounded by an invisible force called a magnetic field. It's created deep inside the planet and stretches far out into space. We don't see it, but it's the reason compasses work and the sun doesn't strip our atmosphere away. This magnetic field doesn't just stop at Earth's surface. It doesn't sit there like a perfect bubble either. The solar wind pushes on it non-stop, stretching it out behind Earth into a long magnetic tail that reaches hundreds of thousands of miles into space, like a tail trailing behind a moving comet. That tail is how Earth's oxygen ends up on the moon. The sun slams into Earth's upper atmosphere, knocking oxygen and nitrogen atoms loose and turning them into charged particles. Normally, they'd drift off into space, but because they're charged, Earth's magnetic field grabs them and sends them backward, down the magnetic tail. Most of the time, the moon is off to the side doing its own thing. But once a month, right around the full moon, it slides straight into Earth's magnetic ponytail. Inside that tail, Earth blocks the harsh solar wind and gives the moon a few days of calm. But it's still moving straight through particles leaking from Earth. Those particles collide with the surface and react with the iron in the soil. Repeat that long enough, and it adds up. Earth loses tiny traces of its air, and the moon quietly collects them using its weak gravity like a slow, patient net. It's like driving behind a dirty truck. Dirt flies off of it, but you don't really notice until it starts sticking to your windshield. The same thing happens on the moon, except, no windshield. We actually have proof of this happening in real time. A Japanese probe called Kaguya was hanging out in lunar orbit, and its sensors spiked when the moon passed through Earth's magnetic tail. It detected a surge of high-energy oxygen ions. Scientists call it the Earth wind. It acts like the solar wind, except instead of being hot particles from a star, it's made from leftovers of our own atmosphere. And this suddenly makes the moon part of a much bigger story. Scientists think this kind of atmospheric escape can help explain what happened to planets like Mars. The red planet doesn't have a global magnetic field today, but long ago it probably did. When that shield failed, its atmosphere had a much easier time leaking away. Studying Earth and the Moon is like watching a version of that process on replay, just in slow motion. And it's not unique. Near the edge of the solar system, Pluto's thin atmosphere is slowly being stolen by its moon Charon. Ooh, larceny in space. Pluto's gravity is so weak that its atmosphere stretches far into space. When those gas particles drift close enough, Charon's gravity simply grabs them. No magnetic field needed, just a leaky planet and a nearby moon pulling the material away. Now, when the Apollo astronauts brought lunar soil to Earth, it was already loaded with hydrogen from the solar wind. The sun sprays the lunar surface with hydrogen, and over time, that hydrogen gets baked straight into the dust. That's the H, but you still need the O2 to create water. The regolith may already contain trace amounts of oxygen locked into minerals and dust, not as ice, but as something that can potentially be processed. It would mean that regolith is not just a nuisance that destroys gear and rovers. For a future lunar base, even small amounts matter. Water is heavy. Launching it from Earth is a nightmare. If the moon can supply even part of what astronauts need, it could make a difference. Now, another cool side effect of this discovery is that drilling into the moon could tell us more about Earth's history. You see, our planet is terrible at keeping records. It's like a giant recycling machine. It's always changing. Tectonic plates grind the crust down and melt it into magma. Winds and rains erode rocks. The air that we breathe now is different from the one that was around 2 billion years ago. Now, we can guess what the ancient atmosphere was like, but we don't have a physical sample. The moon is the complete opposite. It's cold and static. When those Earth particles land on the moon, they get buried under dust and stay there. They're trapped in the crystal lattice of the soil. Think of the lunar surface like an ice core in Antarctica. The deeper we dig, the further back in time we go. If we drill a core sample on the moon, we might, theoretically, find layers of oxygen and nitrogen from 2.5 billion years ago. That is right around the Great Oxidation Event, when microbes first started pumping oxygen into our atmosphere. That could tell us something we don't know. It could prove that life started earlier than we thought. It could show us exactly how a dead planet turns into a living one. That's another answer you can give the next time somebody asks why we should go back to the moon. Also define the green cheese. Hey, just Google it. So, in the end, will the sun be to blame for destroying our planet? Or how about a huge meteorite? Or some kind of disease? Probably not. It seems that life will disappear for a very unexpected reason. Humans, animals, insects, fish, and most microbes will be wiped off the face of the Earth because of oxygen, or more precisely, because of its absence. Recent research has shown that the number of freshwater reservoirs with very low or no oxygen levels in coastal areas is increasing worldwide. Over the past 65 years, 4 times more oxygen-deficient waters have appeared in the world's oceans. What does it all mean? It's likely that life on Earth will vanish much sooner than the sun's energies dries up all the oceans. The end is likely to come in a little more than 1 billion years. But this doesn't mean that the planet will disappear too. The period when Earth is filled with oxygen will make up just about 20 to 30% of the total lifespan of the planet. So we're just temporary guests here. Just think how long that is, 1 billion years. The first Homo sapiens appeared only about 300,000 years ago. That is, the entire history of humanity occupies less than 500,000 years. So relax. A billion years won't pass very fast. By that time, humans won't be on Earth anymore. We might master space travel and find a new planet in the vast depths of space. But why can we lose air? As the sun heats up, the planet gets warmer and warmer, and this heat breaks down carbon dioxide, the gas which is necessary for all plants to photosynthesize. Without carbon dioxide, they can't produce oxygen. With a drop in carbon dioxide levels, the methane content will increase, and this gas is quite harmful to us. Now, this all sounds logical, but this is a secondary reason for the lack of oxygen. The real problem is something else entirely. As the sun becomes brighter, it will begin to heat rocks on Earth, such as granite and basalt. These rocks will start to break down faster. When they collapse, they take carbon dioxide from the air, which warms our planet. If there's less carbon dioxide in the air, Earth should become colder. But there's a problem. The sun will shine more, and its heat will outweigh this cooling effect. So even if rocks take away carbon dioxide, the sun will blaze so much that Earth will still become extremely hot. Next, when the sun shines more intensely, it, along with other natural factors, contributes to the breakdown of granite and basalt. These rocks mix with carbon dioxide and water to make carbonates, which go deep into the Earth. This takes carbon dioxide out of the air, which means plants can't make as much oxygen because they need carbon dioxide to do that. Besides, volcanoes release gases, which also reduce the amount of oxygen in the air. So the sun, by destroying rocks, affects what happens inside Earth and controls how much oxygen there will be in the air. In about 1 billion years, the sun will become so bright that no rocks will be able to save Earth from its heat, and the escaping gases will halt photosynthesis and oxygen production. And then, our planet will return to the state it was in about 2.4 billion years ago, to the time when the Great Oxidation Event began. And this event was much more important than, say, the first Olympic Games or the appearance of humans on the planet. Billions of years ago, there was almost no oxygen on Earth. Instead, there was a soup of gases, such as nitrogen, ammonia, methane, carbon dioxide, and others. Yes, we have these gases in the atmosphere today, but there used to be a lot more of them in the past. It was difficult for any form of life to originate in such conditions. But after some struggle, it succeeded. At first, Earth was inhabited by the simplest bacteria, including cyanobacteria. They learned how to make oxygen using sunlight, water, and carbon dioxide. These bacteria worked for millions and billions of years and made so much oxygen that it began to accumulate in the air. This was what we now call the Great Oxidation Event. It was like a great celebration of life, because with oxygen, new living beings could appear. But by the way, cyanobacteria didn't learn photosynthesis because they were like, oh, let's make oxygen, it's so cool. No, oxygen was just a byproduct. Cyanobacteria wanted only one thing, to get as much energy as possible. And for this, they learned photosynthesis. It helped them store energy using sunlight. They used special pigments to absorb light, and the result of this process was the release of oxygen. This had been going on for hundreds of millions of years, and then, at some point, they made too much oxygen. This oxygen started to spoil other gases that had been there before. For example, it ate a lot of methane. Because of this, Earth cooled down a bit, and the Ice Age began. But that's another story. In short, in 1 billion years, we risk going back to that difficult time. But let's hope that we'll manage to move to another planet on our spaceships or come up with some other solution. And what'll happen to our home planet next? Will new life be able to originate there without so much oxygen? Well, it's possible, but it'll be much more difficult. This will require another source of energy besides the sun. It can be, for example, hydrothermal vents. And by the way, there are ecosystems on Earth that use this type of energy. You can find one of them in the Movile Cave in Romania. Imagine a place where there's little oxygen. It's dark. The sun's rays don't reach there. Over millions of years of evolution, a unique and slightly creepy life has developed in this cave. It was first discovered in 1986, and scientists are still exploring this place. The entrance to the cave is just a small hole in the ground. A narrow tunnel goes deep underground. Inside the cave, the air is filled with hydrogen sulfide and carbon dioxide, and there's half as much oxygen there as on the surface. A human can't stay there without a special mask, but for local forms of life, this is home, and they feel great there. There are several dozen species living in the cave, and many of them aren't found anywhere else on Earth. Here you can see strange little monsters, white snails, white spiders, centipedes with long whiskers, transparent shrimp, and even unknown species of leeches. Since there's no light in the cave, all these creatures don't need eyes. They're blind, but they have long sensitive antennae and paws that allows them to navigate in the space. They also have no colored pigment, so all these bugs and spiders are either white or transparent. But if there's so little oxygen there, and nobody does photosynthesis, then how does all this life survive? It's all thanks to the unique bacteria autotrophs. They absorb carbon dioxide and produce nutrients. These bacteria are food for other organisms, and those, in turn, become food for larger creatures. So a whole food chain has been built in the cave, which provides all the inhabitants with food. Evolution has created a unique ecosystem that exists separately from the rest of the world. It's like a small universe that has developed according to its own rules. However, this universe is not expanding, because all living beings here can't live away from hydrothermal vents and autotrophs. Otherwise, where would they get their energy from? But let's imagine that the sun cools down, almost all the oxygen disappears, and the entire planet gets covered with hydrothermal vents. It's dark, and the air is filled with methane, CO2, and other substances. And somehow, life begins. Even people appear at one point. What would they look like? Pale, thin, and blind creatures with very long arms that help them navigate in space. They have pets, large centipedes or cockroaches that move silently on the ground. People are also quiet because they don't have lungs filled with air to scream. There's silence in the world. People communicate through touch. No one travels. Everyone lives separately next to their hydrothermal source. The whole world has turned into a horror movie in a billion years. Hey, listen up. There's a red alert. NASA supercomputers have calculated that there are only 2,021 years left until the end of the Earth. Our planet is about to… Oh, wait a minute. Oops, I'm sorry. I thought these zeros were a mistake. Well, the research actually says 1,000,000,2021 years in the future. Whew, that's a relief. Breathe normally. Still, this means that our planet officially has an expiration date. And no, this is not science fiction. It's a very real study that shows how, why, and when life on Earth will end. So, thanks to NASA and Japan's Toho University, we can now mark the calendar. It'll happen in around 1 billion years. But what about how and why? Well, even as recently as the early 20th century, scientists still didn't know what powered the sun. One of the first big ideas was that the sun was basically a giant piece of charcoal, just a huge ball of fire burning some kind of fuel. But that was easy to rule out. At the rate the sun puts out energy, it would have burned through that kind of fuel in just a few thousand years. And even back then, geologists and paleontologists already agreed that Earth was at least 100 million years old, if not more. That meant the chemical burning couldn't have possibly kept the sun shining for that long. So, scientists turned to another, more nerdy theory – gravitational contraction. This idea was that the sun shines because of its own weight. Its gravity pulls all the gas inward, squeezing itself tighter and tighter. It's kind of like warming your hands by rubbing them together. We know that gas giants like Jupiter and Saturn are slightly contracting under their own weight and giving off more heat than they get from the sun. So yeah, gravitational contraction, also known as the Kelvin-Helmholtz mechanism, is very much real, but it's not what powers the sun. When researchers did the math, it showed the sun could only shine like that for about 20 to 30 million years. Eventually, scientists learned that the real secret behind the sun's power and longevity was something way more powerful – nuclear fusion. Now, deep inside the sun, it's unbelievably hot. We're talking 27 million degrees Fahrenheit. And it's under crazy pressure because the sun is so big and heavy. All that heat and pressure squashes hydrogen atoms and forces them to stick together. When 4 hydrogen atoms get squished hard enough, they turn into something new, a helium atom. When that happens, a little bit of their mass turns into energy, and that's what becomes sunlight and heat. For centuries, people feared the sun would someday go cold, and that will happen, eventually. About 5 billion years from now, our star will run out of hydrogen, and gravity will take over. But long before that, Earth will already be toast. According to a NASA life extinction prediction, our planet will become a scorched, uninhabitable rock, not because the sun will go out, but because it will burn too hot. It turns out that those old apocalyptic ideas were not completely off. The sun will destroy life on Earth, just not by going cold. But why? Well, it's because, with time, the sun is getting brighter. And I'm not talking about its mood. It releases more energy. It's a slow, natural side effect of the nuclear fusion we just mentioned. Deep in the core, the sun has been fusing hydrogen into helium for billions of years. But as more helium piles up, the core gets denser and hotter. Think of it like a pressure cooker. The more pressure builds up inside, the more heat rises from within. That extra heat speeds up fusion, which means more energy gets released, and the sun starts shining just a little bit brighter. It's not dramatic, we won't notice it in a lifetime, but the future-proof androids we're going to build just might. With time, the extra heat adds up. The sun is already about 30% brighter than when the Earth was born. But life decline is going to happen much earlier, even before the given deadline. As the sun keeps cranking up the heat, Earth is gonna sweat. The extra sunlight raises global temperatures to the point where the ocean surfaces hit around 117 degrees Fahrenheit. That's hot enough to mess with the planet's entire climate system. Water vapor begins to rise from the oceans and accumulate in the upper atmosphere. This causes even more heat to be trapped, creating a thick, humid layer around Earth. Scientists refer to this ongoing cycle as the moist greenhouse effect. The rising temperatures aren't just drying out our planet, they're also harming plants. Plants rely on carbon dioxide from the air to grow and thrive. However, as Earth warms up, certain natural processes can take too much carbon dioxide out of the atmosphere. When that happens, there won't be enough CO2 left for plants to survive. Forests will disappear first, then grasslands, bushes, and even the toughest plants that usually handle extreme heat. This all will lead to oxygen collapse, because plants and CO2 are crucial for photosynthesis. In simple terms, this is how plants use sunlight, along with water and carbon dioxide, to create their own energy and produce oxygen as a waste product. Right now, oxygen makes up about 21% of Earth's atmosphere. But once it drops below even 1%, complex life as we know it will most likely disappear. Earth's biosphere will shrink to just a few microbes and extremophiles, hiding deep underground. But even they won't last long. It's worth noting that scientists ran 2 versions of the simulation, one with life like we have today and one with none at all. Surprisingly, both worlds lost their oxygen at about the same time, around 1 billion years from now. That means plant life and photosynthesis do help, but they're not the main thing keeping oxygen in the atmosphere. It's actually a long-term chemical battle between volcanic gases and rocks that gradually soak up oxygen like a sponge. And even after most life is gone, the heat will keep going, causing oceans to boil. Not all at once, but slowly and steadily, the oceans will begin to evaporate into the atmosphere. But that vapor won't just come back down as rain like it does now. Why? The atmosphere will be too hot and thick for that. Instead, sunlight will start breaking the water apart, and hydrogen will escape into space permanently. Once it's gone for good. Basically, instead of raining back down, Earth's water will slowly leak into space until there's nothing left. Even before the last puddles vanish, life under the sea will be long gone. Once the balance of temperature and oxygen is lost, not even the hardiest ocean life can hold on. In the end, Earth will become something we can barely recognize – a dry, lifeless rock. There will be no water, no oxygen, and no life left. The oceans will be gone. The atmosphere will be thin and toxic. Even the most resilient microbes will have disappeared. However, the sun will still shine in the sky. Earth will keep orbiting just like always. It'll still be a planet, just without life. But long before that cosmic finale, Earth will already be uninhabitable, which raises the big question. So, what could future humans do about all this? Well, escaping sun radiation and extinction might end up being humanity's biggest engineering challenge yet. Maybe we'll build massive space colonies and leap from planet to planet, staying just ahead of the sun's deadly heat. Even if we terraform Mars, making it more Earth-like so we can inhabit it, it'll still be cooking in the same solar oven, just on a lower shelf. Or maybe we'll live in giant rotating space habitats, like O'Neill cylinders, floating mini-worlds with gravity and recycled air, water, and energy to support long-term survival. Those could drift farther and farther from the sun as things heat up. Or who knows, maybe we'll upload our minds to the cosmic cloud or hop into a higher dimension and watch the universe like it's, Netflix. Okay, this is definitely too nerdy, and we're going deep into sci-fi territory. But whatever the solution may be, humankind has a long time ahead to figure out how to survive the eventual end of Earth and life, or maybe even preserve it in whatever form it takes. So listen up. One day our sun will cool down and turn into a white dwarf. But this is not the worst thing for Earth. Before the star cools down, it will grow to an incredible size and arrange Ragnarok for us. Now, in case you don't know, Ragnarok is the fire apocalypse from Nordic mythology. So our star will burn down absolutely everything on our planet. But hey, don't worry, there's good news. This one day will come in 5 to 7 billion years. The bad news, though, is that almost all complex life on Earth will become extinct much sooner, maybe in 250 million years. But there's a small chance that our planet will be ruled by octopuses. Yeah, I know, this is too much news for the first few seconds. So let me break it all down for you, one thing at a time. We all hear about people destroying nature and polluting our planet. This is all true, but even without our intervention, the vast majority of living creatures on the planet will disappear, including ourselves. The reason is natural disasters and weather change. It sounds terrible, but it's not new to Earth. Scientists have found out that there have already been 5 mass extinctions. The last one happened about 65 million years ago, when dinosaurs disappeared. But life won anyway and took on many different forms. The 6th apocalypse may occur within the next 250 million years. Conditions on Earth at this time will be unsuitable for mammals because the level of carbon dioxide will be twice as high. This will happen because the sun will release 2.5% more radiation and it'll get too hot on Earth. The temperature in most parts of the planet will reach between 104 to 158 degrees Fahrenheit, and the entire land will turn into one supercontinent. In regions with high humidity, the temperature will be even higher, and of course, under such conditions, it will be difficult for people to walk in the park and play frisbee with dogs. No one will play with anyone at all. Let's hope we'll have colonized other planets by this time. Increasing solar fluxes will lead to a sharp loss of oxygen in the atmosphere. This means that in about 1 billion years, our Earth will look like the lifeless place it was about 2.5 billion years ago. That is, before the Great Oxidation Event. At that time, the air was filled with methane, carbon dioxide, and other gases. And the planet was inhabited by the simplest bacteria. Some of them learned how to make oxygen from sunlight and carbon dioxide. Throughout billions of years, they made so much oxygen that it became enough for the birth of new, more complex forms of life. And it seems we will return to these prehistoric times. Now, humans can't exist in such conditions, But some complex life forms hiding in the dark depths of the ocean might be able to adapt to the changed atmosphere and become the masters of Earth. These complex life forms are octopuses. There are many species of these animals. Some live in coastal areas, while others dwell in the deep waters of seas and oceans. And some species may be able to survive and create a new civilization. But why octopuses? Because they're some of the most intelligent creatures on Earth, and probably the most intelligent creatures among all the inhabitants of the dark depths. Octopuses can use surrounding objects as tools. For example, they can wear a coconut shell for protection or shelter. In laboratories, they've used various objects to complete mazes. These animals often escape from their water tanks to visit octopuses in nearby tanks. Yes, they have high intelligence, but not in the human sense. Their intelligence is more like a computer. You see, octopuses have neurons not only inside their brains, but also inside their 8 tentacles and large eyes. It's like a big data center, and their limbs sense the environment in exceptional detail, as if they were the brain. Not only their intelligence, but also their physiological properties might help the octopus survive if the apocalypse strikes. Its body has no skeleton. It can squeeze through any hole, slip past any obstacle, and their 8 highly developed limbs allow them to intelligently interact with their surroundings. Crows can bend pieces of wire with their beaks. They can throw stones into the water to raise the water level and get food. But they only have one beak. An octopus with its tentacles has at least 8 times more possibilities. They don't have spines, so they'll most likely build a civilization not on land but underwater, where it's much more convenient to move with such a body. To build a civilization, they'll need to find cheap energy. For example, hydrothermal underwater springs or tides in coastal areas. This will be a difficult task, but it won't be the most challenging thing for creating cities. It's very difficult for them to maintain social connections. By their nature, they are loners, who usually form groups of several individuals. But this is not enough to carry out large-scale construction of underwater urban areas. Parents pass on culture, history, upbringing, and moral guidelines to their children. They spend a lot of time and effort on education. Octopuses don't do this at all. The female octopus passes away shortly after laying eggs. The male octopus has only one mating relationship in its entire life and passes away shortly after the female is fertilized. So, in a sense, octopus cubs are born orphans. It's not surprising that it's difficult for them to build social connections. Over the past 50 to 100 million years, octopuses have not developed a collective feeling, and it's difficult to imagine that it will suddenly appear in the future. Perhaps something will encourage them. Who knows? Some scientists who study octopuses have noticed that over the past 10 years, some octopus species have shown certain social skills. Some live in groups of 10 or more individuals. If humanity doesn't ruin the lives of these animals by fishing and dumping garbage into the ocean, then they have a good chance of succeeding in conquering the planet. But if they fail, then the next candidates might be nematodes, those little white worms. Well, let's hope octopuses win. They seem cuter. They also may achieve a technological breakthrough much faster than we think, because when you have 8 arms, you work much better. Imagine these octopuses leaving Earth and flying to another galaxy, where they meet us humans. Do you think we could become friends? So let's say octopuses become a highly developed civilization that builds cities in the oceans. But they, just like humans, will have to think about colonizing other planets because of the upcoming Ragnarok. The sun keeps heating up and getting bigger, don't forget. Our star is currently in the most stable phase of its life. It has been in this phase for the last 4.5 billion years. But after another 5 billion years or so, the hydrogen in its core will start running out, and then the fun will begin. As hydrogen fusion slows, the core begins to contract. As the core gets smaller, it heats up until it can kick off another round of nuclear reactions, fusing helium into heavier elements such as carbon, nitrogen, and oxygen. Eventually, the sun will turn red and be so gigantic that it will swallow up Mercury, Venus, and possibly Earth. So, it may be Ragnarok not only for our planet, but for the whole solar system. No matter how tough octopuses are, they won't survive such a disaster. Earth is likely to burn down completely. Maybe it'll look like the moon, or it'll completely disappear. What will happen to the sun next? Its energy will run out sooner or later, then it will shrink to the size of Earth and turn into a white dwarf. When a star goes out, it ejects a huge amount of gas and dust. Only the cooling core remains. All those outer layers will be floating in space, forming a beautiful nebula, and our solar system will become unrecognizable. Well, in some ways, it can sound pretty sad and scary, but hey, look at the bright side. Yeah, pun intended. It's going to happen in 5 to 7 billion years, so relax. Humanity has been living on Earth for about 40,000 years. If we compress the entire history of our planet into one 24-hour day, then the history of people will be equal to 1 second. If we achieve such a development in 40,000 years, what'll happen in 100,000 years, in 1,000,000 years, in 1,000,000,000 years? It's hard to predict. So how about going to the park and enjoying the sun at its best? Yeah, bring some sunscreen.
It's official. Official. A day will no longer last 24 hours. Earth's now spinning faster, literally, and our days are going to get shorter. At the moment, it's believed that the shortest day happened on July 10th, 2025. It was shorter not by much, just a fraction of a second, 1.36 milliseconds according to most sources, but still. And all because of the moon's position messing with Earth's rotation, just enough to speed things up. If it turns out to be not a one-time thing and Earth keeps spinning faster, it could be the start of a big mess. All our time stuff like GPS, the internet, atomic clocks, even how countries keep time, depends on the day being 24 hours. But if the planet speeds up, those systems could totally freak out. Clocks would get all out of whack, and anything that needs perfect timing could go sideways. We're talking about more than just a few lost seconds. This could shake up everything. Flights, money transfers, basically how we live day to day. We'll have to rethink how we measure time. Are you ready for that kind of chaos? Now, normally a day is 24 hours, or 86,400 seconds, because that's how long it takes for the planet to do a full spin. But Earth's rotation isn't always stable. A bunch of things influence it, like where the sun and the moon are or how the planet's mass is balanced. Earth is like a giant spinning top, and anything can throw it off rhythm. But our planet has been slowing down for a long, really long time. Because according to scientists, about 1 to 2 billion years ago, a day only lasted 19 hours. Not because the planet was lazy or anything. Nope, it was the moon's fault. It was way closer to us back then. Its gravity had a stronger pull, and that made Earth spin faster. And that faster spin meant shorter days. The thing is, the moon is slowly drifting away from Earth, and as it does, Earth's rotation slows down, and our days get longer over time. But during that billion-year window, something weird happened. The moon kinda just hovered at a certain distance. It wasn't moving out, it wasn't pulling harder. It was like it paused. And that pause locked us into 19-hour days for what scientists are now calling a boring billion. It was a time when pretty much everything on Earth slowed down. Tectonic activity was stable, the climate wasn't doing anything weird, and even life kind of plateaued. Now, let's get into the sciencey part. The moon's gravity controls our ocean tides. That's what slows down Earth's spin. But the sun pulls on Earth too, just in a different way. When sunlight hits Earth's surface and heats it up, that creates what's called solar atmospheric tides, and those can actually speed up Earth's rotation. Right now, the moon's gravitational tides are about twice as strong as the sun's atmospheric tides, which means the moon is in charge when it comes to Earth's spin. But back in the boring billion, the sun and moon were basically in a tug-of-war with equal strength. This phenomenon is called tidal resonance. It's like Earth hit a cosmic pause button. If the moon hadn't backed off, we might still be living in a 19-hour-day world right now. These days, the moon is still drifting away from us, and because of that, our days are slowly getting longer. Until lately, things have gotten weird. In the last few years, scientists noticed that Earth hasn't been sticking to schedule. In fact, it's been spinning faster, and I mean record-breaking fast. Back in 2020, Earth started picking up the pace more than it had since scientists started clocking it in the 70s. Then came July 5th, 2024, the shortest day ever recorded. We lost 1.66 milliseconds. Not a big deal if you're just watching videos on YouTube, but on a planetary scale, it's kinda huge. Now, we get back to July 10th, 2025. On that date, the moon was sitting way up near the poles, very far from Earth's equator. And that changed the game. When the moon is hanging out closer to the poles, it messes with Earth's rotation and makes our days a little bit shorter. That kind of change isn't unusual. Earth's spin has always had some ups and downs. But today, the moon isn't the only factor. According to NASA, human activity is changing how Earth spins too. Between 2000 and 2018, moving ice and pumping groundwater around the planet shifted enough mass that it added 1.33 milliseconds to our days per century. Natural disasters can mess things up too. Remember the massive earthquake that hit Japan in 2011? It actually shortened Earth's day by 1.8 microseconds. Just one quake, one microjolt to the planet's schedule, but the consequences were catastrophic. On March 11, 2011, at exactly 2:46 p.m. local time, a huge earthquake hit off Japan's east coast. We're talking magnitude 9, one of the biggest quakes ever recorded. The epicenter was about 80 miles from Sendai and over 230 miles from Tokyo. Japan's main island shifted 8 feet. Yes, the ground moved and whole cities literally slid, but it didn't just shake buildings and trigger a tsunami. The quake was so strong it redistributed Earth's mass, like shifting weights around on a spinning top. When you do that, the top spins differently. Same deal with Earth. The movement of tectonic plates was enough to tweak the whole planet's rotation. The thing is, the earthquake moved land and shifted Earth's figure axis. That's the axis our planet's mass balances around, by 6.5 inches. That's separate from the north-south spin axis, which we rotate on daily at about 1,000 miles per hour. But still, that shift was enough to make Earth wobble differently as it was spinning. It didn't tilt the entire axis in space. Only stuff like the sun or moon's gravity can do that. But it was still a major shakeup, no pun intended. And it wasn't the first time this had happened. The 2004 Sumatra quake, a staggering magnitude 9.1, sped up Earth's spin and cut 6.8 microseconds off the day. Chile's 2010 quake took off another 1.26 microseconds. Every time one of these megaquakes hit, it's like Earth gets a tiny jolt, spinning just a hair faster. And it might not be over. For example, that March 11 quake unleashed more than 80 aftershocks that were magnitude 6.0 or higher. Long after, some of those aftershocks were still tweaking the day length. It was very subtle, changes in millionths of a second, but real. But the thing is, even the seasons can mess with how fast Earth spins. A geophysicist from the University of Liverpool has explained it like this. There's way more land in the northern hemisphere than in the south. So, during northern summer, trees grow leaves, and that leaf mass moves upward, farther from Earth's center. And it sounds pretty harmless, right? But no, that tiny shift actually slows down our planet's spin, just a bit. Think about a figure skater, arms in, they spin faster. Arms out, they slow down. Same with Earth. When its mass shifts away from the core, it rotates more slowly. So yeah, in the summer, Earth literally chills a bit, spin-wise. Now you don't panic about your day suddenly feeling longer yet. Your clock is still gonna say 24 hours. That's just how our timekeeping works. As for these differences, they're milliseconds. You'd never feel it. But the problem is that over time, it all adds up. If the planet ever spun slow enough that we were off by more than 0.9 seconds, then we'd have to do something. That's when the International Earth Rotation and Reference System Service steps in. These are the people who keep tabs on Earth's spin. And if things drift too far out of sync with our clocks, they throw in a leap second to fix it. Yep, they literally add a second to the clock every now and then to keep Earth time on track. It's like the universe's version of a software update. In any case, with the moon slowly drifting away and Earth calming down, the fact that our planet is suddenly picking up speed, even just a little, makes experts and ordinary people raise their eyebrows. It's a reminder that even something as basic as a day isn't set in stone. The planet's moving quicker. Time is literally slipping. Something's shifting.
For the last few decades, Earth has had an interesting coincidence. The northern and southern hemispheres have reflected almost the same exact amount of sunlight back into space, but new data from NASA shows that this symmetry is collapsing. The planet is becoming lopsided in a way we haven't measured before. Why is this happening? And will it change the weather we rely on? Well, let's talk about that. If you tear the map in half at the equator, you get two drastically different pieces. The northern hemisphere is the crowded side, having around 68% of Earth's landmass. It has massive continents of North America, Europe, and Asia, the sands of the Sahara, and the snows of the Himalayas. The southern hemisphere is the complete opposite. It is a water world. Aside from Antarctica and a slice of South America, it is almost entirely a deep, dark ocean. In fact, there's a spot in the South Pacific where you can travel for thousands of miles without hitting a single patch of dirt. This area is home to the oceanic pole of inaccessibility, better known as Point Nemo. It's so remote that if you sailed there, the nearest humans wouldn't be in Chile or New Zealand. They'd often be the astronauts on the International Space Station passing overhead. It's one of the emptiest places on Earth, surrounded by thousands of miles of open ocean. Now, when sunlight travels 93 million miles and hits Earth, two things can happen. It either bounces off the planet and escapes to space, or it gets absorbed. That's because of the phenomenon called albedo. It works exactly like your wardrobe on a scorching day. Lighter surfaces act like mirrors, bouncing the sun away to keep you cool. Darker surfaces are like sponges. They soak up that energy and turn it into heat. Now, humans have actually figured this out on a smaller scale. If you didn't know, many traditional houses on the Greek islands are painted bright white. It's like a form of ancient air conditioning. The white paint reflects the intense Mediterranean sun and helps keep the inside cool. Cities are now trying a similar trick. Places like Los Angeles have spent millions of dollars coating black asphalt streets with a special gray surface to boost the city's albedo. By making the ground a lighter color, street surfaces can cool by about 15 degrees. Now, on a much bigger scale, planetary even, ice, snow, and bright deserts act like mirrors, bouncing back the light, while oceans are the opposite. They soak up the rays and store that energy as heat. So, according to physics, the land-heavy north should reflect more sunlight. The ocean-heavy south should absorb more. Meanwhile, when looking at Earth from space, one half should look brighter than the other. So for decades, NASA has tracked Earth's energy using a system called CERES, short for Clouds and the Earth's Radiant Energy System. These satellites measure how much sunlight arrives and how much leaves. This is how we learned that Earth is cheating around the albedo rule. Now, think of Earth's atmosphere as a giant planetary mixer, constantly pushing heat between the north and south to keep it from piling up in one place. According to the latest data, that mixer is starting to fall behind. When scientists looked closely at the CERES data, they saw a clear split forming between the hemispheres. The northern hemisphere is now holding onto more of the sun's energy than the southern hemisphere. Specifically, the north is gaining about 0.3 watts per square foot per decade more solar energy than the south. Yep, that sounds microscopic, but multiply that by every square foot of the Earth's surface, and you have a massive engine of heat that could make the weather unpredictable. Now, you would expect clouds to push back by reflecting more heat to space, but the data shows that the response hasn't been strong enough, so the extra energy keeps piling up in the northern hemisphere. Now, this is a big deal because heat is what makes the weather move. Hot air rises and pushes wind and storms around the globe. If one side of the planet creates more pressure than the other, those wind patterns have to shift. So it's not just that the weather is getting hotter, it's that it physically moves to new places. You've probably heard of the geographic equator, the invisible line running around the middle of the planet. But there is another equator related to weather. It's called the thermal equator. Think of this as a giant collision zone. Imagine pointing two powerful fans at each other. Where the airstreams meet, the air often gets forced upward, building what could look like a moving wall of rain. Scientists call this zone the Intertropical Convergence Zone, or ITCZ. It marks the planet's thermal equator. Sailors had a better name and knew it as the doldrums. They knew it as a zone where winds cancel each other out. Pirates in the 1700s were terrified of it. You could get stuck there for weeks, just floating, waiting for your drinking water to run out. The system acts like a planetary thermostat. It likes to hang out where the heat is. For most of human history, it stayed right in the middle. But if this imbalance keeps growing, it could nudge the thermal equator north over time. Now, you might be thinking, so what if the rain belt shifts a few hundred miles? Well, history gives us a pretty striking example. About 6,000 years ago, this rain belt sat farther north than it does today. At the time, much of what we now call the Sahara wasn't desert at all. It supported lakes, grasslands, wildlife like hippos and giraffes, and thriving human communities. Rock art from the region even shows boats and swimming scenes. As Earth's orbit slowly changed, the rain belt migrated south. Over time, rainfall faded, lakes dried up, and the landscape transformed into the Sahara we know today. The trigger was different, but the mechanism was the same. When the planet's energy balance shifts, the thermal equator moves, and the rain moves with it. This is a huge deal because rain is incredibly important for food production. It waters the regions that grow our coffee, our chocolate, not our chocolate, yep, and the crops that billions of people eat. If that belt chases the heat and moves north, the rain goes with it. The jungles in the south could dry out, while cities in the north would get hit with floods they were never built to handle. But the air is only half the story. Down at lower elevations, the extra heat triggers a chain reaction. Remember the t-shirt analogy? Much of the northern hemisphere depends on bright snow and sea ice to reflect sunlight away. But as temperatures rise, that low-altitude ice melts. When the white surface disappears, it exposes darker ocean water or bare ground underneath. This creates what scientists call a feedback loop. As the ice melts, it reveals the darker ocean or land underneath, and that dark ground absorbs more heat, which can cause even more ice to melt. It's a cycle that could make it progressively harder for the region to cool itself down naturally. Meanwhile, the oceans take their time responding. Global currents act like a giant conveyor belt, moving warm water around the globe to balance energy. But this system is delicate. It only works when the water's temperature and saltiness are just right. When the North hoards too much heat, it throws the currents off. And if the belt slows or reroutes, the effects don't hit overnight. They unfold gradually over decades or even centuries. But finally, is this just a temporary glitch? Or is the Earth settling into a brand new pattern? Right now, scientists can't tell for sure. Maybe the clouds will finally show up and fix the balance. maybe the oceans will move the heat around and save the day. But if the North keeps gaining an energy advantage, the weather maps we rely on might change for decades or centuries. If that's the case, many places will have to rethink their daily life. Those not used to rain would suddenly feel cheated, while the value of raincoats, umbrellas, and white t-shirts skyrockets.